Okay, thank you, Patrick, and thanks to everyone for being here. So my thesis is titled Topological Inference from Measures and Vector Bundles, and this is a work I did under the supervision of Marc Gliss and Frédéric Chazal. So I would like to start with a short introduction to my field, topological inference. In topological inference, we aim at studying datasets that are presented as point clouds. So let me explain with two examples how one can obtain a point cloud from a scientific experiment. The first example comes from biomedicine. So the authors study breast cancer. They extract tissues, infected tissues from people infected by breast cancer, and they analyze these tissues, and they obtain 262 variables, genomic variables. So one is able to convert one patient into 1 point in R to the 262. The second example comes from chemistry. So the cyclooctane molecule admits several spatial conformation, and you can encode the spatial conformation of a molecule with 72 variables. So we can transform a molecule into 1 point in R to the 72. Now, let's take a bunch of patients and a bunch of molecules. We obtain point clouds. And as you can see here, these point clouds lie close to some shape, some underlying geometric object. And the goal of topological inference is to understand these shapes. So this is where my thesis starts. I aimed at building mathematical methods in order to understand these shapes. And we will study these shapes via algebraic topology. So algebraic topology is a way to go from the wide world of topological spaces to the rigid world of algebraic structures. If you have topological space as an input, you obtain algebraic structures such as vector spaces or algebra. And these structures contain information, topological information about your spaces. The issue here is that this theory has been thought for continuous shapes. So if you want to use it on the point cloud, you will not obtain interesting information at the algebraic level. And there is a way to overcome this issue. It is called persistent homology, and this is the main tool that I used in my thesis. And the idea is that we won't consider the point clouds as they are, but we will build filtrations on them. So let me motivate this construction. One of the most basic questions in topological inference is the following. Say there is a submanifold, a circle here, M, and X, a point cloud that we suppose close to M. The question is, can I infer the homotopy type of M from the observation X? And there is a very simple construction that allows to answer this question. It consists in thickening X. For every T, I define the T thickening of X. It is a set of points of the ambient space that are a distance at most T from X. So these are 3 examples of thickenings. And the last one is a circle, topologically. We have a theorem about that. Under some geometric assumptions on n and x, there exists a whole interval where one can select values of t such that the T thickening of x has the homotopy type of M. So this is nice, but in practice, we won't be able to access to this interval, and we won't know these values of T. So we will consider them all, and the collection of all the thickenings is called the check filtration. So now let's do some algebra. For every thickening, I will compute its homology groups, here over Z over 2Z. So as the filtration grows, the groups evolve. At some point, we have the homology groups of the circle. And there is a bit more of a structure here, because the check filtration comes with inclusion maps. And at the algebraic level, by applying the homology functor, we obtain linear maps between these homology groups. And the data of the homology groups plus these linear maps is called a persistence module. And this is the main object of persistent homology. So let me give you a clear definition. A persistence module is the data of a family of vector spaces indexed by the real line, and a family of linear maps between each two of them. And these linear maps have to satisfy some naturality conditions. There is a very handy way for building persistence modules. It's based on filtrations. So a filtration is simply an increasing collection of subsets of Rn. Now I pick any I, a natural number, and I apply the ith singular homology functor. That gives me a persistence module. This is the same construction that before with the check filtration. So there has been a lot of work regarding the algebraic structure of a persistence module. And what we know is that when they are regular, here pointwise finite dimensional, persistence modules can be decomposed into a sum of indecomposable ones. And these indecomposable persistence modules are described with an interval. They are called interval modules. And the set of intervals that describes a persistence module is called its barcode. And the barcode completely describes the persistence module. So for instance, if V is a persistence module, its barcode could be this collection of intervals. And we like to draw it like that. There is a very nice interpretation of barcodes. So here, I took X, a point cloud, that is close to the circle. I considered the check filtration of it, and I computed the barcodes for the 0th homology and first homology. So H0 is in red, and H1 in green. So the barcode tells me the homology of my thickening at each step of the filtration. If I pause here, I have one red bar. That means my H0 is of dimension 1, and one green bar. My H1 is of dimension 1. And moreover, in these barcodes, we are able to track these cycles and see how long they survive in the filtration, how long they persist. So for instance, this cycle here persists until the end of the bar, when my thickening becomes a disk point. So we have 4 objects here. The subsets of Rn, the filtrations we build from them, the persistence modules we obtain from filtrations, and their barcodes. And each of these objects are endowed with distances, the Hausdorff distance for subsets of Rn, the interleaving distance for the filtrations and the persistence modules, and the bottleneck distance for the barcodes. And what is great is that all these distances are related. We have the very important isometry theorem, which states that the bottleneck distance between 2 barcodes is equal to the interleaving distance between the persistence module from which they come from. And as a consequence, though it has been proven before, we have the stability theorem. It says that if I have 2 subsets of the Euclidean space, I build their check filtrations, I build the persistence module, and then I consider their barcodes. The distance between their barcodes is bounded by the distance between the subsets. An image? if I have a circle and I consider the check filtration, I would obtain these barcodes. Now, if I have only this point cloud, the same construction will give me these barcodes that are close to the initial ones in bottleneck distance. So this is really important in practice, because it means that even if we do not have access to the whole shape, we are still able to obtain homological information from a point cloud. Okay, so this is the initial setting of persistent homology. You have a point cloud, you build filtration, persistence modules, and you compute the barcode, and you hope to read topological information in this barcode. However, the hypotheses to apply this method are a bit restrictive, and the work of my thesis consisted in expanding the possibilities of application of persistent homology. It is divided into 3 works that I'm going to present one after another. The first one is about point clouds that contains anomalous points. And in this case, this usual setting cannot be applied. So let me show it to you. Okay, so this is a joint work with my advisors, Frédéric Chazal and Mark Gliss, and our Japanese collaborators, Hirokazu Anai, Yuichi Ike, Hiroya Nakoshi, and Yuhei Umeda. So this is where we were. If I have the circle, I consider its check filtration, I obtain barcodes that gives me the persistent homology of my circle. If I have a point cloud that samples the circle, I can still consider the check filtration, its barcodes, and I recover homological information in these barcodes. You can see one long green bar and one long red bar. Okay, and now let's say I have a sample with anomalous points. This check filtration does not look like a circle, right? And this can be seen in the barcodes. I cannot see clearly the homology of the circle. So there is a need to modify this check filtration in order to obtain informative barcodes. And so the method we propose is based on 2 ingredients, a weighted version of the check filtration and the distance to measure. And the end, it will look something like that. Okay. Weighted check filtration. So if I have a point cloud X, the check filtration, so it is the collection of thickenings, right? It can be written as a set of XTs, where XT is a union of balls centered around every point of X and with radius T. Now, let's pick a map F from X to R. That is called the weighting map. And I will define the weighted check filtration to be the collection of sets Vt, where Vt is a union of balls centered around every point of X, but with radius T minus f of X, T minus the weight. If you have a ball of negative radius, it is the empty set by convention. So basically here, for a ball to appear around X, we have to wait for T to go above the weight, f of X. So we postpone the apparition of the balls in the filtration. And in practice, what you would like to do is to have a weighting map F that takes high values on anomalous points, so that anomalous points will appear late in the filtration. This is something that has already been studied some years before with this radius function. So we decided to generalize it. The actual weighted check filtration depends also on the parameter P. And the parameter P controls the radius functions. Right. So now we have to find a nice weighting map. And a map that does that is the DTM, the distance to measure. The distance to measure is based on a measure, and you will understand soon why this is interesting. So say we have a measure for the moment, mu, and a parameter m. The DTM is a map from the Euclidean space to R that is defined as a quadratic mean of this quantity delta that is written above. So for instance, here, an example where mu is the empirical measure on X, this point cloud, and I drew the values of it. And as you can see, the DTM takes small values close to the circle and high values on the anomalous points, right? This is because the DTM is sensitive to high density areas and low density areas of the measure. So there is an important result about it. Say I have two measures, mu and nu, on the Euclidean space. I can compare the DTM associated to them in a subnorm. And the subnorm of the difference of the DTMs is bounded by the Wasserstein distance between mu and nu. The Wasserstein distance, this is the optimal transport distance between measures. So this is a stability result that says that if I do not observe mu directly, but a close measure nu, in the sense of Wasserstein distance, the DTM are still close to each other. And this is a very interesting point of view for us, because the Wasserstein distance will play the role of the distance we want between for a problem. Let me explain to you. First, how can I convert a set into a measure? I give two examples here. If X is a finite subset, I can consider the empirical measure. If M is a compact manifold, I can consider the uniform measure on it. So now we can transform subsets into measures and compare these measures in Wasserstein distance. And this is really nice because the Wasserstein distance is not too sensitive to anomalous points in the measure. So for instance, here, X and M will be far away in Hausdorff distance, but the corresponding measures will be close to each other in Wasserstein distance. And this is what we want because we want to use X to estimate M. Okay, so now we have the weighted check filtration, the DTM, and a measure point of view. So let's define the DTM filtration. The DTM filtration is based on three parameters, a measure, mu, a parameter m, and a parameter p. And it is defined as the weighted check filtration, where the parameters are, for the set x, the support of the measure, for the function, the weighting function f, the DTM of parameters mu and m, and for the parameter p, the parameter p. So I denote it w, mu and p. Explicitly, it is a collection of wt's that are union of balls. And it looks like that. So as you can see, balls grow at the beginning close to the circle, where the DTM is low, and then they appear on anomalous points. And we have a very nice barcode next to it, where we see two large bars, a red one and a green one. That is, we see a circle around it. And we have a theorem which explains that. I will start with the case p equal to 1. So I need to define a quantity C. C of mu is defined as the supremum of the DTM on the support of the measure. The quantity C has been designed to certify the regularity of the measure. Basically, if mu is close to a uniform measure on a submanifold, C will be small. If mu contains outliers, C will be high. Okay, and then the theorem says that, say you have two measures, mu and nu, and you want to compare the DTM filtrations based on mu and on nu. We need an auxiliary measure, nu prime. The only assumption is that the support of nu prime is included in the support of nu. Then the interleaving distance between the DTM filtrations W mu and W nu is bounded by this sum. So if you want this sum to be small, you will choose nu prime such that nu prime is close to mu and nu in Wasserstein distance, and such that nu prime satisfies C of nu primes is small. For instance, if mu will be the uniform measure on the circle and nu where this noisy sample with anomalous points, I will choose nu prime as nu without the anomalous points. Because nu prime as the empirical measure is still close to mu and nu, and nu prime does not have anomalous points, so that C of nu prime is small. When P is larger than 1, it is a bit more complicated. We have to modify the quantity C. So now the diameter of the support appears. And moreover, the bound we obtain is not between the filtrations, but within the persistence modules. So we have a stability at a homological level. Okay, and this stability result in Wasserstein distance guarantee to us that we can apply the DTM filtrations on point clouds with anomalous points and still obtain informative barcodes at the end. So this is it for the DTM filtrations. So we studied here a different context than the usual context of persistent homology. In my second work, I studied another context again. It is when the point cloud is sampled not close to a manifold, but close to an immersed manifold. Let's go. So let me give you some context. For the problem, we suppose that we are given the immersion of a manifold. So there exists an abstract manifold, M0, that is immersed into the Euclidean space via an immersion U. And the image of the immersion is denoted M. Some examples. If M0 is a circle, an immersion of it could be the lemniscate. If M0 is a Klein bottle, an immersion of it could be this classical drawing of the Klein bottle. This is a picture of an exchange road in Dallas. So this is just a bunch of lines of roads, right? But seen from the top, you can see a bunch of intersecting lines. So this is an immersion. Okay. And the problem is the following. I do not observe the abstract manifold, but the immersion. And I want you to give me the homology groups of the initial manifold. And a weaker, harder question could be, I only have access to a sample, potentially noisy, of this immersion. So we will use persistent homology, of course. But if we were to apply the check filtration to the immersion, we will not get the homology of the abstract manifold. We will get the homology, of course, of the image, which is different in this case. So what we'll try to do is to add dimensions to our space in order to try to lift this object, to remove the singularities, to unknot this object. And this, in this higher dimensional space, we will use persistent homology and obtain barcodes, where here, on this interval, you can read a circle, right? So U is the immersion. We will consider a new map, U check, which goes into Rn times Rm. So I add m dimensions to my space. And I want to design a map, F, such that U check is an embedding. And our choice for F is the tangent space map. So to at each point x0 of the abstract manifold maps the tangent space of this manifold at x0. This is a nice choice of F for at least two reasons. One, under a mild genericity condition on the immersion, U check is an embedding, so that the image of U check is a submanifold. And moreover, from this point of view, as you can see, we are actually looking at the tangent bundle of M0. And this is an interesting point of view that we will study a bit more in my third work. Some notations. So U is the immersion. If I have a point x0 of the abstract manifold, I will denote x the image of x0. And I will denote T x0m the tangent space of M0. MRN is the space of matrices, n times n. And I will denote PTXM, the projection matrix on the tangent space. Okay. And now our Lift space is Rn times the matrix space. The matrix space is the dimensions we add to the space. The lifted manifold is denoted M check. And so it is a set of pairs, a Euclidean point, and the projection matrix on the tangent space. Okay. And at last, the lifting map, U check, goes from the abstract manifold M0 to M checked, is defined just here. So we want to estimate this submanifold, M check. But we only observe a sample of the image, right? So say that X, the observation, is this nice sample of the lemniscate. We have to estimate the projection matrices. And we will do so with local covariance matrices. So a local covariance matrix depends on two parameters, a base point and a radius. And it is defined as a mean of tensor products, like that. And the local covariance matrix is a good estimator of the projection matrix on the tangent spaces. So I naturally consider X check to be the set of pairs, a Euclidean point, and a local covariance matrix. And I hope for X check to be close to M check. But this is not true, because the local covariance matrices are biased next to the intersection of the immersion. And as a consequence, my set M check and X check won't be close in Hausdorff distance. So you can see anomalous points in the center. So this is where the local covariance matrices does not estimate well the projection matrices on tangent spaces. So we have some anomalous points, but if you recall what we've done before, in a measure point of view, a few anomalous points, this is okay for us. So we should adopt a measure point of view again on this problem. So let's go. From now on, M0 will be endowed with a measure, mu0. If I push forward this measure via the immersion U, I obtain mu. I define mu like that. And in this context, we are not, we are observing mu or a closed measure, nu. If I push forward mu0 with the map U check, I will define a measure mu0 check on the lifted manifold. Okay. And what happens here is that this measure, the lifted measure, mu0 check, admits a simple description in terms of test function. It is defined like that with this equation. So now I only observe nu. I will lift nu in the lift space with this equation. So I simply replaced the projection matrices with the local covariance matrices adapted for measures. And I hope, again, that nu check and mu0 check are close, and they are in Wasserstein distance. So for this result to work, you have to suppose that the initial Wasserstein distance between the measure and the ground space is small, and that the parameter R of the local covariance matrices is small too. Then the P Wasserstein distance for any P is bounded by this term. Fine. And as a consequence, we can estimate M check, the lifted manifold, that is to say M0, because they are diffeomorphic. So how can I obtain the homotopy type of M check? I have a measure nu, I lift it in the V space, and here I consider the DTM, the distance to measure on nu check. And there exists some sublevel sets of the DTM that has the homotopy type of M check. We can also go a bit further. If you want to do precedent homology, once I am in the lift space, I could consider a DTM filtration on this lifted measure. So this is an example where X is a sample of the Olympic rings with some anomalous points. I consider the empirical measure on it. I lift the measure into the lift space, and I consider a DTM filtration. And as you can see here, at the beginning, I have 5 red bars and 5 green bars. That is, I observe 5 circles, right? And 5 circles are exactly the abstract manifold that underlies the Olympic rings. Okay, that's it. So what we've estimated here is the tangent bubble of my manifold. And this is a nice invitation to consider more general vector bundles, because vector bundles comes with interesting algebraic invariants that are contains more information than simply homology. So this is what I've done in my third work. So let's go back to the menu. Let's consider vector bundles, okay? So I'd like to introduce the problem on this slide. So until now, we considered the problem of estimating homotopy types or homology. However, in some cases, homology is not a fine enough invariant to study topological spaces. For instance, the torus and the Klein bottle over Z over 2Z admits the same homology groups. So we cannot distinguish them through the eyes of homology, and this is something we would like to do in practice. There are, in algebraic topology, a lot of other interesting invariants that allows to differentiate such spaces. And what we will study here are the Stiefel-Whitney classes. The Stiefel-Whitney classes, in general, are defined for any topological space, X, endowed with a vector bundle structure. So for every integer I, we have the ith Stiefel-Whitney class, and this is an element of the ith cohomology group of X. It is denoted Wi of Xi, where Xi is a vector bundle. And a natural problem is, can I estimate the Stiefel-Whitney classes of my vector bundle from a sample of it? To do so, we will need a handy definition of vector bundles. So let me present the usual definition of vector bundles. Over a space X, a vector bundle is the data of the total space, E, that surjects on X, and such that the fibers are vector spaces that satisfies some local chirality conditions. Two examples. If X is a circle, a vector bundle over it could be the normal bundle. So on top of each point of the circle, I have a vector space. Another example is the Möbius strip, also called the universal bundle of the circle. Okay. So in order to propose another definition, I will need two objects. First, the Grassmannian. If I have any vector space V, the Grassmannian GD of V is the set of D subspace of the set of subspaces, linear subspaces of dimension D of V. Okay. And I also consider R infinite. R infinite is the space of sequences of real numbers that are 0 from some point. So in vector bundle theory, there is a famous correspondence between this first definition and this second definition. Defining a vector bundle is the same as defining a map from a topological space X to the Grassmannian over R infinite. So this is true in the if X is paracompact. If X is simply compact, I can also consider maps from X to the Grassmannian over Rm, where M is large enough. So this will be our definition of vector bundles from now on. Okay. This definition is really nice because thanks to it, we can define simply the Stiefel-Whitney classes. So let me recall you that the Grassmannian over R infinite has a really simple cohomology algebra. It is the algebra generated by D elements, each of degree I. So Wi is of degree I. Now, if I have a vector bundle, Xi, from X to the Grassmannian over R infinite, I can take the image of these generators of the Grassmannian, and these images exactly are the Stiefel-Whitney classes of the vector bundle. This is a way of defining the Stiefel-Whitney classes. So for instance here, the normal bundle of the circle, I have a map to the infinite Grassmannian, actually G1 of R2 is enough here. I look at the cohomology of the Grassmannian, and if I push this class W1 into the cohomology of the circle, I obtain the Stiefel-Whitney class, the first Stiefel-Whitney class of the normal bundle of the circle, which is 0 here. Okay, so let's adopt a persistent point of view on that. Let's say X is any subset of Rn endowed with a vector bundle structure. So I have a map Xi from X to the Grassmannian over Rm. And I will do the same construction as before. I will consider the lifted manifold, here the lifted space. I consider X check to be the set of pairs, a Euclidean point, and a vector space. Okay? So this is a subset of Rn times the Grassmannian. We want to linearize that, so I embed the Grassmannian into the metric space via the natural embedding that maps any subspace to its projection matrix. And now I can see X check as a subset of Rn times the metric space. So X check now is a subset of a linear space, and I can consider the check filtration of X check, the thickening filtration. And something great happens here. In the check filtration, I can define vector bundle structures. Each of these thickenings can be endowed with a vector bundle structure. It is simply defined as follows. If I have any T, I have a map Xi T from the T thickening of X check to the Grassmannian that is defined as if you have a point XA of the thickening, X being a Euclidean point and A being a matrix, I associate the projection on the matrix of the matrix on the Grassmannian. Okay. So we can naturally define the persistent Stiefel-Whitney classes. Take any integer I. The ith persistent Stiefel-Whitney class of X check, the lifted space, is simply the collection of all the Stiefel-Whitney classes of my thickenings. There is an issue, though. These maps, Xi T, are not well defined for every value of T. This is because we have to make sure that A, this matrix, does not lie in the medial axis of the Grassmannian. So actually, there exists a maximal value of T such that the persistent Stiefel-Whitney class is defined. That's how it is. Hopefully, this maximal value of T can be computed in practice thanks to this lemma. Okay. Which was not very important. So I propose a summary of the persistent Stiefel-Whitney class that I call the live bar. If you consider any persistent Stiefel-Whitney class, define the set of values of T such that it is non-zero. This is the live bar of it. And I represent it like that. So the live bar goes from 0.2 to 1. And what happens is that this live bar is an interval. It means that if the class is non-zero at some point, it will be non-zero until the end of the filtration. Two examples. The normal bundle of the circle, its live bar is the empty set. The Mobius strip, its live bar is the whole filtration. So this persistent Stiefel-Whitney class is non-zero all along the filtration. Okay. So to finish, let me present two results about it. The first one is a stability result that says that if I do not observe the exact vector bundle, but a sample of it, a closed sample, then the Stiefel-Whitney classes will be closed. And as a consequence, the live bars too. Still the example of the normal bundle of the circle. The live bar is 0, is the empty set. If I have this sample, the corresponding live bar is also the empty set. This is a Mobius strip. The live bar is a whole interval. Now, this noisy sample give me this live bar for the first persistent Stiefel-Whitney class. And as you can see, it is non-zero from 0.3, and these two live bars are closed. And the last result is a consistency result, which says that if I have a sample of a vector bundle, there exists a whole interval of the filtration on which the persistent Stiefel-Whitney class actually is equal to the usual Stiefel-Whitney class of my initial vector bundle. Two experiments here. This is a torus, a sample of the torus, and I consider the normal bundle of it. I computed the live bar of its first persistent Stiefel-Whitney class, and I obtained this. It is the empty set. This is the same example on the Klein bottle. And as you can see, it is non-zero from 0.3, which is consistent with the first Stiefel-Whitney class of the normal bundle of the Klein bottle, because it is non-zero. Okay, that's it. These stability and consistency results certify that we can apply this method in practice, and we can be sure to obtain informative homological information. So I presented to you my three works that are connected, as you've seen. Of course, I hid some details, in particular concerning the immersed manifolds. The usual geometric tools of subsets of Rn were not adapted for immersed manifolds, so I had to develop a notion of normal reach that was suited to deal with immersed manifolds. Concerning the Stiefel-Whitney classes, so I proposed an algorithm where I use simplicial approximation. So this is a very usual technique in theoretical mathematics. But the simplicial approximation and the star condition cannot be applied in practice. So I proposed the notion of weak star condition that plays the role of the star condition in practice. And more generally, for each of these works that I hope will be used in practice, I proposed concrete lines of code that are available on my webpage. Okay, and last word about perspectives. So something that really interests the community at the moment are the stratified spaces and the ideas, these lifting ideas that I developed, I'm quite sure can be applied to these more general spaces. And besides, so still these ideas could be used to study more general fiber bundles. And I think that this could be useful in theoretical mathematics, but also in the application. For instance, I love to try to triangulate, have some ideas about that. Try to triangulate the Grassmann manifolds. This is something we need in the application for design of algorithms. And that's it. Thank you.